And welcome back. Today we're going to talk about one-way analysis of variance, which is really just a variation or an extension of the two-sample t-test. So here's the formula for the two-sample t-test, where we have the difference between two means. We have sample 1, sample 2, our experimental group and our control group. And we divide that by the standard error of the difference between two means, symbolized by S subscript x bar minus x bar. So that's the t-test, and the basic concept being tested there is we draw two samples, and our null hypothesis says that our two samples came from the same population. So maybe one sample has a mean that's around there, okay, and another sample has a mean that's around there. And so our null hypothesis says both of these samples came from this one population. However, if these means are very far apart, and where that cutoff point is what you have to look up in the table for. That shows you that 0.05 cutoff level. If those means are so far apart that they would only happen in the same population fewer than 5 times out of 100, just by chance alone, then we reject the null hypothesis and we assume or infer that in fact one of the means came from a different population, that it's more likely to come from here than it is to come from here. So that's the basic concept of the two-sample t-test. Hopefully you're back up to speed on that. Let me clear some of this. Okay, so we're going to do something similar with the with one-way analysis of variance. And let me back up a little bit about one-way analysis of variance and explain what's happening. The basic difference is with analysis of variance, instead of just having two samples that we are comparing, we will be comparing 3 or more samples or 3 or more groups. The null hypothesis being that they all came from the same population, and the research hypothesis being that there are at least 2 separate populations, and maybe if we have 3 groups, maybe there's 3. So this one has its own mu, and this one has its own mu, and this one has its own mu. So that's the what a one-way analysis of variance is doing, is it's extending the two-sample t-test to 3 samples, or 3 groups, or 4 groups, or 5 groups. And let me clear some of this information away and give you a little bit more background on the reasoning behind it. So here's the basic thought behind the analysis of variance. And let me put some curves up. So here's one curve, and it's going to have its own mean. So suppose that we draw a sample, and this is what the sample looks like. It's got its own mean, its own standard deviation. And then we happen to draw another sample, and we give it a different manipulation or different level of our independent variable, and that sample is not going to be identical to the first. It's going to have its own mean and its own standard deviation. And then we have a third group with its own mean and its own standard deviation. So in a two-sample t-test, we would have just had 2 curves, right? Group 1 and group 2. Now we've got group 1, group 2, and group 3. That's a 3. All right. So here's the basic theory behind analysis of variance. If the null hypothesis is true, that is, the levels of our independent variable or our manipulation has no effect whatsoever on behavior. And what that's saying then is that these 3 means, this one, and this one, differ only because of sampling error. Okay? It's just like taking groups of 5 students from the same statistics class, and their means aren't going to be identical. Their mean on the exam, for example, are going to be identical. They'll be different just because of sampling error. So we expect then, if the null hypothesis is true, that the difference between those two means is just due to sampling error. The difference between those two means is just due to sampling error. And the difference between those three means is just due to sampling error. That's if the null hypothesis is true, those differences are just because of sampling error. Okay? Now, similarly, if you remember, not everybody scored at the mean. Individuals for group 1 show variation all over. Individuals in group 2 didn't score exactly at the mean. Some scored way out, but most scored way in the middle. And same thing for group 3. Now, individual variability of this sort, the reason why one person differed from another inside their own group or within their group, that is just error. Unfortunately to you guys, to statisticians, individual variability, why one person differs from another, is just error. Okay, and that's the flat definition. It doesn't matter if the null hypothesis is true or false or anything in between. Individual differences is error. So now, if you were following along, we've got two measures of error. Okay, individual variability from one person to the next is error no matter what. That's the definition of error. Then the differences between groups is also error, but only if the null hypothesis is true. Okay? So hopefully, maybe you're starting to get an idea here that if we compare the differences between groups, that's the part up here, the differences between groups, to the differences within groups, if the null hypothesis is true, then these are both measures of error, and those values should be very similar, right? The error between groups should be fairly similar to the error within groups, if the null hypothesis is true, and both of those are measures of error. However, if the null hypothesis is false, that is, our independent variable is actually causing a change in the way people are behaving, well, the null hypothesis, the independent variable doesn't change individual differences. It doesn't change why one person scores higher than another. All it's going to change is the overall pattern from one group to another. So if the research hypothesis is true, then the difference between groups, that is, this part up here, is no longer just error. It's not just sampling differences. It's in fact due to something real. And in statistics we call that our treatment, or our independent variable. Instead, or in contrast, the individual differences from one person to the next hasn't changed at all. That's still error. So let me clean things up a little bit here. So let me state it a different way. Let's the null hypothesis assumes that our three scores, or three samples, or three groups, right? Here's sample 1, here's sample 2, and here is sample 3. Now they differ. The null hypothesis says that they differ only because of sampling error. In other words, the assumption is that all three samples came from one population with its own mu. And we just happen to get three groups that differ by a little bit because of sampling error. That would be the null hypothesis. And that means that this group differs from mu just because of sampling error. That group differs from mu just because of sampling error. And that group differs from mu just because of sampling error. So if the null hypothesis is true, and all three of these groups came from this population, then this variability, or differences from the mean, if you remember the definition of a variance is the squared difference from the mean, is just due to sampling error. And I already said that individual variability, why one person differs from the next within a group, is already just error. So we've got a known source of error or definition of error, and that's individual differences. And if the null hypothesis is true, then we have a second estimate of error. And so what we do in ANOVA is we create a ratio. We divide the error obtained between groups, why one sample differs from another sample. We divide that by the error within groups, which is the individual variability. Or said another way, we take between groups variability and divide that by within groups variability. And once again, if the null hypothesis is true and the three groups did come from that one population, then these two scores should be very similar, and we should get a score that is, error divided by error. Anything divided by itself should be 1, or it's actually close to 0. However, if the null hypothesis is false, and I'm going to clean things up here. Okay, if the null hypothesis is false, then what we're really saying is that at least one, but possibly all, of these means came from a completely different population with its own mu. Each sample came from a different population because of the independent variable manipulation that makes them a different group altogether. So that's the difference between if the null hypothesis is true. There we go. You can see in this big mess. The point is all three groups are believed to have come from the same single population. But if the null hypothesis is false and our manipulation does cause a change in behavior, then we are inferring that the groups came from different populations with different mu's. So the next important concept in understanding ANOVA is how do we calculate or get between groups variability and within groups variability? Well, that comes down to, again, our understanding of if I conducted an experiment, and let's just say we had 3 groups of 30 people. So all total, 3 groups of 30 people, our total sample in the study would be 90 individuals, but there would be 30 in each group, right? And 1 would have 30, and 2 would have 30, and 3 would have 30, okay? Now, if I just gave you a sample of 90 scores and had you calculate the variance, this is what we're going to call our total variance. And total variance would be, the variance score from all 90 individuals. But we can actually break that up into 2 things. We can break that up into variability between groups. That is any effect of our manipulation, our independent variable, how we treat group 1 different from group 2, which is treated different from group 3. That would be between groups variability, and plus error. And error, as we discussed earlier, is just individual differences, difference from one person to the next. So if we're treating our 3 groups differently in some way because of our IV, and that IV is having an effect, then our manipulation is going to contribute to why some people differed from others out of that whole set of 90. But if our independent variable has no effect whatsoever, then that's really not going to contribute everything, and the whole reason why one person differs from the next is just due to individual differences or error. So what we do in ANOVA is take that total and break it up into this between groups variability and within groups variability. And the example that is in your slides shows you how to do that, and I'll walk you through that experiment now. Hopefully you are following along with the slides or the lecture notes, and I'm on slide 7 right now, where the title of it is Example. And the question that we're investigating is, under what conditions are students most likely to do their homework? And the 3 conditions that we have are that the homework is required, or the homework is offered for extra credit, or it's just made optional. You don't get any benefit to it, just do it if you want to. So how many IVs are there in this experiment? Well, hopefully you answered just one independent variable. That one independent variable is the instruction for homework. Next question. How many levels of the independent variable are there? Well, there are, hopefully you said, 3. Homework was either required, it was extra credit, or it was optional. There we go. So don't confuse the levels of the independent variable with the independent variable itself. The independent variable is like the umbrella term. What is varying from one group to the next? Well, the instructions given are varying. And how many different variations were there? There were 3. So the variable is the instructions, and the levels are the number of different types of instructions given. Okay, so what is the dependent variable here? Well, since we asked under what conditions are students most likely to do their homework, then our dependent variable is going to be the completion rate. How many people completed the homework under each condition? So that's the overall design of the experiment. Now, what is the null hypothesis? Remember, the null hypothesis is signified by H sub 0. I'll just write it here. H sub 0 is that instruction, I'm going to do it in shorthand, has no effect on completion rate. Has no effect on homework completion rate. Homework completion. In contrast, our research hypothesis is that instruction does affect homework completion. Sorry for my sloppy writing here. But now you have a firm understanding of this experiment. We're going to vary the instructions on homework and measure the completion rates. The null hypothesis says there will be no difference, or rather, if there is any difference between the completion rates, it's just due to sampling error. Everybody otherwise completes their homework at the same rate. Our research hypothesis says no, instruction does matter, and that people will behave differently. That is, they come from different populations depending on the instruction that they're given. Okay, before we go into some actual calculations in this example, I want to go to the next slide on the lecture notes and take a little bit of time out where we can discuss some of the vocabulary. So what you see on the slide, it says example, doing homework. I brought up the formula for the variance, which you see here. The variance for a sample is s squared, which in the numerator is the sum of the difference between each score and the mean squared, divided by n minus 1. Now, that, as I said, is also known in ANOVA circles as the mean square. I don't know why I just moved that. As the mean square. Not mean as in angry square. It's not like this. That's a mean square. But rather mean as an average. Because the formula is the average, because we sum something up and divide by the number of somethings, of the squared deviations of scores from the mean. So the mean square means the average of the squared deviations, which is the definition of the variance. So let me clear the ink here, and I want to move this aside. A little bit more about the mean square, or the variance that we will be comparing in the analysis of variance, is the numerator and the denominator. Now, if we look at the numerator here, the calculation is where we sum up the squared differences of each score from the mean. So another name for the numerator is the sum of squares. You can read that. The sum of squares, whereas we've already discussed down here that n minus 1 is very simply the degrees of freedom. But that's a new term that we probably haven't come across until now, the sum of squares, and it's just referring to the top half of the variance formula. Now, in analysis of variance, if you remember, I said that we will be comparing the estimate of error between groups to the amount of error within groups, that between to within ratio. So what we'll be doing is calculating the mean square for the average variance, I guess you will, of the difference between the groups in our experiment, and compare that to the variance within the groups of our experiment. And that's the notion of analysis of variance. We're comparing two variances which, if the null hypothesis is true, they're both estimating error or sampling error. Whereas if the null hypothesis is false, then our between groups variance is going to reflect something more. It's going to affect or reflect the effect of our independent variable, whereas our within groups error is just going to be that, just individual differences or error. So if the null hypothesis is true, they should be very similar, the between and the within variability, whereas if the null hypothesis is false, we should see not only individual differences affecting the between groups variability, but also the effect of our independent variable. So the numerator will be larger than the denominator. And now that the experiment is basically set up, I'm going to stop this video because we're getting close to being out of my time limit on it, and I will start part 2 of the lecture on analysis of variance in the next video. So I will see you over there.